Hey, good evening, everybody. Let's get started. It's 6 p.m.
Hello, Professor.
Maybe for some of you, it's good morning, I guess.
6 a.m. So, yeah, good morning here.
Okay, so let's see. So we are in, let me see what is the schedule. We are in day 5, which is about the lecture 4. You are supposed to review that before coming to the class. And yeah, we'll. Is there any question? I see one from Rahul. I'll go to that definitely. So Rahul, do you want to know specific about the shift operation? What's your question there? You put something on the discussion.
Yeah, so for the shift operation, what does it do? What's its purpose?
Oh, okay. So
Yeah, in the lecture, what I understood is that it kind of indicates the number of bits. I mean, it indicates how many bits ahead should the
mhm.
pointer go ahead for to execute the next command, to read the next command. That's kind of what I understood, but I just wanted to confirm it.
Shift is an operation. Like, have you used the shift operation at the high level program?
I mean, the only shift operation I've used is on my keyboard for caps lock. I mean, yeah.
Let me actually go and explain that shift operation for everyone. Uh, I'm sharing my whiteboard, so you can also go there and check. No, not this one. Where is my whiteboard? Okay, so so we are talking about this shift operation. So on the high level, let's say you can write some program like this, like in a C, or I believe in Java also it supports that. Something like this. Uh, Integer, let's say a equals 20. Then you can write something like b equals left shift by 2 bits, by 2 position. So these two are, let me put another example. See, right shift by 2 position. So these operands, these operations are basically called a bit shift operation. So these operations. Now, what does it mean? So internally in computing system, every value is represented by bits. For example, let's assume this is, we are talking about a 8-bit computing system. So their values will be represented with 8 bits. So let's try to just make that 8 bits. So with the study of the number system, now probably you know this 20 will be represented as something like in a bit position 0, so 1, 2, 4, 8, 16. 1, 0, 1, 0, 0, 0, 0, 0. Okay, so your variable A is represented like this. Variable A's value is represented like this. That means the memory address corresponding to this high level variable will have this bit pattern in the memory 0, 0, 0, 1, 0, 1, 0, 0. Now, next operation, this one, what the intention is here is to make every bit shift to the left 2 position. So that means this bit will be shifted into this position, this bit will be shifted into this position, and so on and so forth. So this will be at this will be at this will be at this will be at this. Now what will happen to this bit? This will just be thrown away. Okay, thrown away. It will go out of scope for this assignment. And now what will happen to these 2 positions? These 2 positions, a bit value will be inserted as 0. So essentially, after this left shift operation, your bit pattern will become like this. So your initial, so I'm just doing some color code. So this will be inserted from outside world like 0 and followed by 0, 0, 1, 0, 1, 0. So this becomes the value assigned to B. Now similarly, for this one, where it is trying to right shift 2 bit for on the bit pattern that belongs to A, what will happen is just the reverse thing, the other way, right? So this will be thrown away, this will be thrown away, and then this bit will move to this position, this bit will move to this position, and so on and so forth. This one is going to here, this one going to here, this one is going to here. And what happened to the rest of these 2 positions? 0 will be inserted into here. So that means at the end of this operation will result in a bit pattern like this. These are the 0 inserted from outside world, and then we have 0, 0, 0, 1, 0, 1, 1, 0, 1. Yeah. So this becomes your value of C. Okay. Now what is these values looks like in a decimal? So if you remember your number system conversion, 8-bit conversion you need to make, this one will be definitely, I can say it is this is 1, 2.
C will be 5.
Yeah, this is 5 and this is 80, I think. This is 80. Let's see. This is 0. This is 1. This is 0 also. 0, 0. Then this is 0, 1, 2, 3, 4. 2 to the power 4 and 5 2 to the power 6. So 2 to the power 4 is 16. This one is 16. And this one is 32, 64. 64 plus 16 is 80. And also, if you notice, this is basically what we are doing A by 4. Sorry, other way. This is A multiplied by 4. And this one is A division 4, integer division. So in fact, this is a faster way of doing multiplication and division operation, given that your multiplier or divider is a power of 2. So in general, if you are multiplying some number like this, a into 2 to the power n, what all you need to do, take this bit pattern, okay, and left shift by n. And if you are doing something like a divided by 2 to the power n, this operation, this is nothing but a right shift by that amount, and which is basically a fast operation than really doing a multiplication or division in the hardware level.
Yeah, like adding and removing zeros for multiplying, dividing by 10.
Come again, Rahul?
I just noticed that this is similar in base 10. When you multiply with 10 or divide by 10, you add or subtract zeros. We're kind of doing
Right,
the same thing over here,
right, exactly.
multiplying by the base value.
Mm-hmm. Right, but it is like more like like conception wise, it is you are as if shifting the bits position in the bit pattern. In terms of that, it is not like padding up zeros or one. It is basically shifting your position inside for a representation.
Thank you. That clears that one the question I had.
Okay. Is there any other questions from anyone on these or anything else? Now let me launch a poll then. Let me see how many of you have done reading of the materials. Let's take like a minute, maybe 30 seconds to poll on this.
Wait, Professor,
Yes.
do the lecture videos not cover the reading material?
Yeah.
Okay, because I've only been watching the lecture videos. I haven't been doing the reading.
Okay. Yeah, but yeah, they are basically like for some reading makes more sense than watching video. For some people, watching video makes more sense than reading. So uh, they're kind of on your choice basis. And I would say like you do the both basically. Sometimes in the video I explain little bit, explain more than what has been written in the notes.
Are the reading notes above the video, the PowerPoint slides?
Yes, those are slides with some notes.
Okay, that's the thing you're asking us to read.
Yeah.
Okay.
All right, so we have these. Let's see. Let's share this result with you guys. That's good. All of them 77%. Great job, class. Like other 20%, please keep up. Queries. You have some queries. You haven't noted them. And I don't have any question, 41%. That is a kind of worrisome sign for me. You need to ask yourself, like, are you clear on the topic? And yeah, and I hope I'll get more and more questions out of those topics. Okay, anyway, let's do some different thing tonight. Let me see. I will create some group randomly tonight and try the breakout room, okay, with some problems, to solve. So let me first see how can I make a breakout room. Okay, breakout rooms. Create breakout room. Okay, how many of you? About 23, 3, maybe 8 rooms. Okay. And then I'm going to post these two problems onto the whiteboard. So either I'm sharing the whiteboard. You can follow that or just access the whiteboard directly. You have the link in the Canvas page for this class whiteboard. So let's see, share. Okay, now. Okay, there are two problems. One is this, and two is this. Okay. Okay, let me first explain this problem to you guys. So what is given is that there is a 32-bit 1.6 gigahertz, that is the clock speed is 1.6 gigahertz. Computing system has half-watt addressable memory with 40 bit address bus in it. This memory takes 2 clock cycles to complete read or write operations. So it's not 1 clock cycle, it takes 2 clock cycles. And also 1 clock cycle to consume the data from the memory. The processor takes more clock cycle to consume the data from the memory. During the operation with a single instruction, the processor generated 2.5 million instruction. Okay, this one is 1 million is 10 to the power 6. So we didn't copy correctly. Let me just say, this is, how do I change it? Maybe I'll do this. 10 to the power 6. Continuous read and write operation. 40% of the memory operations are read operation and 20% of the write operations request are successor to read operation request. That means it's a back-to-back read-write scenario. So you need to calculate the clock period in nanosecond unit. You need to calculate memory size in the gigabyte unit. And you need to calculate how long it will take to complete this 2.5 million memory access in the millisecond unit. And the second problem is a processor execute instruction using 5-stage instruction execution cycle that we described in previous classes. This processor run on this 1.6 gigahertz clock. How long this processor will take in the millisecond unit to execute 5 million instruction. So these two problems, let's solve in a group. I have just assigned randomly some breakout room for you. And this will be, let me see. You guys will discuss, chat, etc., etc. Okay, 15 minutes. Okay, and that breakout room session will start. Do you guys have any question, anyone?
For the second question, do we assume that the clock cycle is 1?
Yes.
Okay.
Memory takes 1 clock cycle, etc., etc. Okay, so I'd also suggest to like solve this, put this on a Word document or something that you can share with the class if you want. Yeah, and it will, yeah.
Where can we access this question, or like this Jamboard, or the?
You go to the Canvas page, first page. It has somewhere there. It has this link to this whiteboard.
I see. Checking it out.
Okay, I'm opening the room for you. I believe yeah, most of you have 3 in groups, 2 groups has 2 in it. Okay, your time starts now, and let's have a 15-minute work yourself with others and come up with solution.
Professor, I don't have a room invite.
Okay, Kevin, let me assign that to you. Okay, just a minute.
Hey, Professor,
Yes,
could you enable screen sharing permissions?
I will. Now, do you need it in the group? I thought in the group it is already on.
I mean, we can all look at. No, it's not. It needs to be enabled. It's not on by default in the breakout rooms.
Okay, okay. Let me see if I'm turning on now. Try it. Okay.
All right, cool. Hey, Professor. I'm heading to room now.
Okay, I think let's get back to our discussion. So any volunteer who will go to explain the first one or did completed? No?
We just did the part, first part A and B in our group.
Okay, sure. I have the share screen option on, so if you want to share screen. Rahul, you are going to explain?
Well, you're muted.
I see. I was muted. Thanks for pointing that out. So for the first part, we had to find the clock speed, the clock period, how long it takes to complete one clock cycle, and that can be found from the clock speed. So 1.6 gigahertz. We take the reciprocal of that, and we'll get the clock speed as 0.625 into 10 to the power negative 9 seconds. That's the clock period. In nanoseconds, that'll just be 0.625 nanoseconds.
Okay, that's good. How about the next one?
Calculate the memory size in gigabyte unit. The answer we got was 2199 gigabytes, which feels like a lot for just plain memory. And the way we did it is, so this memory has a 40-bit 40-bit address data bus. That means there are 2 into 10 2 to the power 40 different addresses, or that's the upper limit of the addresses. It can be less than that,
Okay,
but that's the upper limit. So that's how many addresses are there, and each address is a 16-bit address, because that's the half word addressable memory.
okay.
We just googled what half word is. I mean, we tried to find, look to our notes, and found half word is a 16-bit instead of a regular 32-bit memory space. So that gives us 40, 2 to the power 40 times 16 bits, and then converting to get how many gigabytes that is. 1 gigabyte is 8 into 10 to the power 9 bits. So we just divide. So we divide 16 into 2 to the power 40 divided by 8 into 10 to the power 9. And the result was 2199 gigabytes.
Okay, this is a little bit different than what I expected, but okay, good explanations though. Let's see, anyone else want to have a chance on this 2B answer, different answers? No? Okay. Then I will show you about that one. 1B, okay. How about the next one, 1C? Have anyone done it? Any group done that? No? Okay, how about that next problem, problem 2?
I tried it.
Okay, Andrew, yeah, sure. Why don't you?
So if it's a 5-stage instruction cycle, or instruction execution cycle, and there's 5 million instructions. That means it's 5 million times 5. So there's 25 million clock cycles essentially, because each instruction takes one clock cycle. And then if the processor runs on a 1.6 gigahertz clock, means the clock speed is 0.625 nanoseconds, same as our previous one. So you multiply 25 million by 0.625 and you get, mine was 15,625 nanoseconds. If you reduce that down to seconds, it would be about 0.015625 seconds.
Right. But it was asked for the millisecond unit. So
Oh, milliseconds units, my bad.
yeah, it will be 15 points.
15.
Yeah, exactly. Thank you very much, Amar. So that means, let me try to show you how that B and C to be solved. Let me again go back to my whiteboard. Okay. Now you see that first one, Rahul, your team was on the right approach, but somewhere you messed up with the units. So let's see. This one is 2 to the power 40 from the address bit, okay, multiplied by 2 bytes. Okay, 2 bytes is a word, half word is a 2 byte, and full word is a 4 byte, and 1 byte is 8 bit. Since we are going to the gigabyte unit, let's concentrate on that, onto the gigabyte unit, and this one would become like 2 to the power 41 bytes. Okay, so 2 to the power 40 multiplied by 2, it's an power increase there. And let's speed it up like this: 2 to the power 11 multiplied by 2 to the power 30 bytes. Let me explain why I actually split this up like this. Because 2 to the power 30 is gig. In a memory calculation, memory size calculation, 1 kilo is 1024, which is 2 to the power 10. 1 meg is 2 to the power 20. 1 gig is 2 to the power 30. So it is nothing but 2 to the power 11 gigabyte. Yeah, which is a lot, Rahul, as you mentioned, this is a lot, but this is just a theoretical and mathematical question. So this becomes like 2048 gigabyte. So you see, Rahul, probably somewhere you guys messed up with the unit conversion. Do you see the problem?
We did mess up the unit conversion. We took 10 to the power 9 bytes as 1 gigabyte. Yeah, I just gone on the SI units. We have 10 to the power 3 is 1 kilo, 10 to the power 6 is mega, 10 to the power 9 is.
In fact, in the IT world, information technology world, in a very rough calculation, 10 to the power something, that SI unit is used frequently. But since we are in the hardware class, we will go with the exact amount of units. It's a power of 2. 2 to the power 10 is kilo, 2 to the power 20 is mega, 2 to the power 30 is giga for the memory sizes. Okay. So now,
I have a quick question.
Yes.
So 2 bytes is still like, so that's what half word is, right?
Yeah.
And that's like still the same as 16-bit?
Yeah, that's a 16.
Yeah, okay, thank you.
All right, now the next one. So this one is, let's see.
Professor, just to clarify, but we multiplied 2 to the 40 times 2 because the clock cycle is, or the memory takes 2 clock cycles, right?
Oh, no, we are talking about the size. So it is all coming from this half-word addressable memory. So the concept is something like this. Like, let's say each address, let's say, contains certain number of memory, like sorry, certain number of bits. So in this case, each address is a 2 byte. So it is 2 byte, right? And you have then you need to see how many such addresses are there, right?
Mm-hmm.
And that's basically 2 to the power 40. So entire memory has like 2 byte of container for for 2 to the power 40 container there. Backward. Yeah. So now this this axis has 2 bytes and this axis has 2 to the power 40 different container to store the memory. So this become this one, 2 to the power 40 multiplied by 2 bytes.
I see. Thank you.
All right, now the next problem. Let's do the next problem. Oops, where is this? This one was 1B. Now 1C, I see this problem in this very simple way. So it said that it takes each of the read and write operation takes 2 clock cycles. Let's not worry about the extra clock cycle needed for back-to-back read, write, and all this stuff. Let's say there is like without any delay, any extra cycle, how many clock cycle will be needed? So there are 2.5 million memory operation, and each take 2 clock cycle. Okay, so this is like 10 to the power 6, 2.5 million multiplied by 2 clock cycle, right? This many cycles is needed. Now let's compute the extra clock cycle. So extra clock cycles comes from your back-to-back read and write operation. So back-to-back read and write, how many are there in terms of out of this 2.5 million? So you see that out of 2.5 million, there are 40% of the memory operation read operation. That means 60% of the memory operations are the write operation, right? And out of that 60%, 20% of the write operation requests are the successor of the read operation. That means your extra cycle needed is 60%, which is 0.6, multiplied by, out of this 60%, 20% of them is causing this extra 1 clock cycle, because in the problem it says the processor takes 1 clock cycle to consume the data. So there, from there, we know how many extra clock cycle we need to add on top of this 2.5 million operation. This many cycle is needed. So this one is about, this is like 5 multiplied by 10 to the power 6. And this is like 0.6, 0.2 to 0.2.5. It is about 0.3. 0.3 multiplied by 10 to the power 6 cycles. So that means total cycle needed is So we are adding these two, this one and this one, which is 5.3 million. So let's do that. So this is like 5.3 million cycles. That means total time needed is that many cycle multiplied by that clock period, which we computed as 0.625 nanosecond, which means this is essentially nanosecond and 10 to the power 6. If you put them together, it becomes a millisecond unit. So it is simply 5.3 multiplied by 0.625, which is 3.3125. If you use a calculator, you will come to that millisecond. So your time needed to calculate this, time needed to complete that 2.5 million operation would be 3.3125 millisecond. Question?
Yes, I have a question.
Sure, Rahul.
So with the extra clock cycles we calculated, those extra clock cycles come from processing the information that's read, processing the data that's read from memory. Is that correct?
Right. Mhm.
So why is it that the information is being processed only in the cases where there's a write operation following the read operation? Because
So,
shouldn't every read operation be followed by processing of the memory,
so
processing of the data that's read?
it is not like a processing as per se. It is more about your like processor is consuming that data, right, during that cycle. So end of the read cycle, memory is sending the data,
Hmm.
and processor need to register that data within another clock cycle. That's the one cycle for consumption. So
Okay.
back-to-back read wouldn't have that problem. If you go back to the previous second day or maybe third day lecture, please
Yes.
review that video. We actually describe that why these back-to-back read write will have an extra clock cycle to be added there. Okay, please review that lecture one.
So
Yeah.
yeah, okay. So I remember that lecture, and so when we say consume data, this takes one clock cycle to consume data. It's referring to the extra bit at the end that's needed. That's the consumption of data.
Right. So it is coming from the fact that memories is producing that data at one time point, and
Hmm.
processor needs one more clock cycle to register in that data. So that
Okay.
means during that one's time, during
Hmm.
that time, no one can override any data on that data bus.
Okay, and that time period is the time where the consumption of data is happening.
Right.
Okay, I see.
Processor always consume the data, but how much cycle will be adding extra, that really depend on back-to-back read write, because back-to-back read or back-to-back write or write read, it does not need to have that extra wait time because of this timing relation between these different digital signal. So you need to refer back to our previous discussion on that memory and processor data exchange timing diagram.
I see. Okay, thank you. That clears it.
All right. So if we don't have a question, then let's take 5-minute break and we'll be back at 7. Okay, let's get back. I have posted 2 more problems from the number system study. Please take 5 minutes to solve that problem, and let's hope someone can explain the answer by 5 minutes. Okay. Okay, who wants to volunteer for 1A? No one? How about 1B?
I can do 1A.
Okay.
So
Do you want to share?
yeah, I was just wrapping up the final calculation.
Okay.
So this looks like a base 7 number system. There are 7 different symbols.
Right.
So each position, I mean, yeah, okay. So it's a base 7 number system, and we've got the decimal equivalents. Do is equivalent to 0, Re is equivalent to 1, Mi is equivalent to 2. Now for the first one, the number that we are given is Mi, Re, Do, which if you're looking at the power 7 thing, it will be Mi multiplied by 7 to the power of 3, Re multiplied by 7 to the power of 2 plus another Re multiplied to 7.
Right.
And placing in the decimal values, you get 2 multiplied by 7 to the power of 3 for Me, plus, yeah, Re is just 1, so 7 to the power of 2 plus another 7 to the power of 1, and that gives 742.
Exactly. Thank you very much. So how about anyone else on the 1B? So it is the reverse transformation. Or 1A, is there any anyone has any question on that, what Rahul said? Okay, the 1A is 742. Now for 1B, what you need to do is basically keep on dividing this given number with base 7. Why base 7? Because it has this 7 notation for representing the number, do, re, mi, fa, sol, la, ti. So doing that, maybe I can share the whiteboard once more. Okay, so this one would become like, so each time what you need to do is to keep on dividing stuff like this. Okay, let's see. So it becomes like the number given is 1045637 45673, right? 73. Base 7, because it has this 7 symbol, the number base is 7. So what we do, we basically compute the quotient and remainder for this division. So if we calculate this correctly, it will quotient for this guy will become 149381, and remainder for this would be 6. Now 6 is equivalent to T. So let's put that, like it has this do, re, mi, equivalent is 0, 1, 2, 3, 4, 5, 6. So remainder 6 means it's the symbol T, and then we pick up this quotient and further divided it by 7, which gives you the quotient of 21340 with remainder of 1, and 1 is Re. And then you basically keep on repeating the same process And this will give 3048 with remainder of 4, which is so. And then 3048 divided by 7, which will give 435 as a quotient and remainder as 3, which is far. And then 435 divided by 7, which will give 62 as a quotient, 1 as a remainder, which is ray. And then 62 by 7, it will give you 8 as a quotient, 6 as a remainder, which is t. And then 8 divided by 7 equals, sorry, no, 6, sorry, 8. 8 divided by 7, which is quotient 1, and remainder 1, which is ray, and 1 divided by 7, quotient 0, remainder 1, it is ray. So that means we need to now write it from the down to up, this direction, and answer would be ray, ray, t, ray, fa, so, ray, t. Okay. How about the next one? Number 2. Anyone wants to go for that? No? Okay, this is interesting.
Oh,
Yes, Andrew.
so I thought that 4-bit 2 complement only goes from +7 to -8 in decimal representation.
Uh-huh.
So
Exactly.
you cannot represent value 12.
Yes. So that's the answer. It's not possible because the range of a 4-bit 2's complement representation goes from lowest -8 to 7. So it cannot represent a value 12. It cannot represent any value outside that range of -8 to 7. Thank you very much, Andrew, for that one. All right. Now, okay, now let's quickly look. We have like 2 minutes. Let us quickly look what is upcoming for the next lecture. Let me see, share the screen. Okay, all right. So modules. So we are on the second module, right? Module 2. Lecture 4 is done for today. Lecture 5, let's see what is there. Lecture 5 talks about, so it has quite a lot of videos there. Please make sure you watch them and understand concept. There are quite a lot of concept to pick up from this lecture. So you need to be very careful. So the topics are very simple, 3 topics: executable generation, assembler, and linker and loader. We'll focus mainly on the assembler in this class. Executable generation and linker loader will just touch upon the concept. Executable generation is more like a compiler system class topic, and linker loader is more like an operating system or system software study. We'll mainly focus on the assembler. And you can refer to this chapter A2 again of computer organization and design by the Patterson if you want to know more about those topics. Let's see what is there. So we started with the big picture, how the executable is generated from a assembly level source file, that concept. Then we go from there with the linking of things. And then this is the main topic that you need to focus on, assembler. How, given an assembly program, assembler actually generate the machine codes. That's what is being discussed here. You don't need to know anything about assembly programming at this point. Just focus on how an assembler tool, given the program, translate it into machine code. So we talked about this symbol table generation concept there. Please make sure you understand that. And then we went to the machine code generation, given that in the previous lecture, we already talked about from a given assembly code, how you can actually generate a machine code please refer to today's lecture that you're supposed to do. And then we talked about a little bit on the local and global levels. So this concept is very important. Please make sure you understand that. And then we talked about a little bit of theoretical discussion on one-pass assembler, how it looks like and what is the pros and cons of this. This is more like a theoretical perspective. And then we talked about some object file format. Again, this is just an information. We won't be dealing with the object file format in the rest of the semester. This is mainly focused for the compiler classes. And then additional facilities. This is important to know. Please make sure you understand that, especially the data layout, how different data layouts you can do with the assembly statements. And also macro is another strong concept. Please make sure you understand that concept of the macro, the usage, and what is the underlying mechanism of macros in an assembly program. So this is important. And then we talked about some, which we call a pseudo instruction concept. Please go through that. That is also important concept to be grasped. And then we came back to the linker loader discussion once more, little bit, but I hope this will be taken in the operating system class in more details. All right, so I think that's all for tonight. We are 2 minutes overboard already. Please make sure you reviewed all these concepts before coming to the next week